For the last major topics, because we're moving into light at this point. So the last major topics that we have, I've actually got PowerPoint slides, and you guys do have access to all of these PowerPoint slides. Part of it is just because it's easier for me to draw with the PowerPoint slides than it is necessarily to draw with the individual type of, there we go, that's going to be a little bit better, individual type of activities that are there. So looks like everything is available to everybody. I'm not seeing a whole lot in there. I'm in the process of grading everything, trying to make sure everybody knows exactly where they stand before we go into the Thanksgiving week. I got quite a bit graded last week. In fact, I think almost everything is up to date for Physics 2. So I'm working on that. But we're gonna run quickly through these slides. You have numerous videos. I did get the videos uploaded from a variety of other things, so hopefully that you've got that. And so we'll just dive in unless somebody has a quick question. All right, seeing none, we're gonna make that transition from optics. So with magnetism, what we found was that the electric field would generate a magnetic field, and a magnetic field would generate an electric field. And through some interesting mathematics and trying to explain that phenomena, you could argue that light was a particle or that light was a wave. And that's where we started this semester. We started this semester looking at waves, but there are a lot of things that we can actually use a particle description to make more sense. And there are other things that use a wave description. So if you go back into the history of how we develop electricity and magnetism, how we develop the topics that we deal with now, it was really an interesting argument between those 16 and 1700s, where we start looking at, is light a wave or is light a particle? Newton says, hey, it's going to be a particle, and we're going to look at particles. Huygens comes out, and we saw this early on in the semester, that we saw that any individual point on a wave front could generate a new wave. And so the Huygens principle came through, and we actually have seen that with sound waves. Well, Young started looking at reflection and refraction and interference patterns with light, and said, hey, those interference patterns only seem to make sense if light is a wave. And we get those interference patterns like we see with ripples in a tank or ripples on a pond. And so they actually saw it. And then Maxwell finally gave us the mathematics that allowed us to be able to say, hey, we have a predictable way to come up with the speed of light. So that's where we come from. And then finally, Einstein shows that light can behave both like a particle and a wave. And that's where we get our quantum theory comes through, and we start talking about wave packets and wave descriptions and those kinds of things. So Young did the double slit experiment, looks very much like ripples in a tank. And we get a nice slit here, and then we get a double slit, and we're going to generate a diffraction pattern. Now, we utilize this theory when Young did it with light, but we utilize this with X-rays in order to determine crystallography. So we actually see that. And you can go to this YouTube video and you can actually look at wave tank simulations. But Young did this, and this is kind of the fringe pattern that he would see. We would get that double slit, and it's based off of those two slits are going to have light slightly out of phase with each other. So that phase idea that we saw with AC motors comes into play, and we start looking at those items, but we get these maximum and minimum patterns that are available. So what we know is that in some experiments, light behaves like a wave. In other experiments, light behaves like a classic particle. But the electromagnetic theory provides explanation of both that propagation and interference. And we can utilize that particle idea to help us do things like ray optics, which is how we're going to finish the semester. We're going to utilize it for ray optics. So the biggest diss in all of science is that there was an argument in the French Academy in the early 1800s that said, if light truly is a wave, then you'd see this spot. And he was convinced that that spot wasn't going to be there. And he argued that it wouldn't be there. And this was how you were going to show that light was a wave or a particle. And it turns out the spot is there. This is Poisson's spot. Poisson actually postulated, he actually described the potential experiment and said, well, I don't think light's a wave. I think it's a particle. And no, so this spot's not going to show. And Fresnel goes out and actually does the experiment and names it Poisson's spot. So this actually definitively said that light can behave like a wave because we got that spot. So it's kind of an interesting one. Now, what we know now, and based off of Einstein and Planck's theory, and so those of you who've already had chemistry know this part of the story, is that we now can deal with photons. And photons, like any other wave, all waves carry energy. And it's just how that energy is moving. And so a photon is a packet of waves, which was what we have. We get a wave packet, and that's what's going to allow us to have both that particle nature and that wave nature. And it's going to allow us to go back and forth between frequency and wavelength and energy. So my photon is really going to carry that energy. And we've got that Planck's constant. So those of us who've taken chemistry and know and play with that idea of my energy levels and that quantum theory that we get for identifying our orbitals that we have in the atom, we can now go back and look at those hops between those energy levels in terms of light, whether that's an X-ray, whether that's a UV ray, or whether that's a visible ray, that we can get that. And we know that the energy is going to be related to Planck's constant times the frequency. And this gives us both natures of light. It encompasses the particle nature as well as the wave nature. So now we start saying, all right, we're going to look at this and we're going to look at the behavior of light. How does light truly behave? So the easiest thing to look at first is refraction and reflection. And you guys do have that refraction laboratory where you're going to be taking a glass of water and putting a pencil in and demonstrating refraction. So you're looking at that refraction part. And we know that reflection is I can have the light hit and reflect off and come back. And then refraction is where light goes into the other medium, whether that medium is water, whether that medium is another electric, an item of, say, some other fluid. We have those changes. So in reflection, part of the light bounces back. In refraction, it passes into the next medium and it's going to bend. And both processes can occur at the same time. This is where we're going to go. We're going to approximate our light as a ray. We're going to use an arrow to represent light. And it's going to allow us to follow that wave front. And we're going to use that to approximate. Now, what's really cool is that particle nature of light will allow us to geometrically come up with the solutions to our problems. And I will actually show you a reflected problem. You've got a reflection problem. You've got some other examples in Blackboard that you can see it. But basically what that ray is doing is it's representing our wave front. And we're going to represent that with an arrow, and we're going to allow that to be there. So our wave front is a surface passing through points of the wave that have the same phase and amplitude. So we're going to define an incident ray. That's the ray that's going to hit my surface. And when it encounters that boundary, it can either be reflected or refracted. And so here is the reflection. So we're going to use this as our definition of refraction. This is our specular reflection, and it's coming from a smooth surface. And so here you've got a laser pointer that's bouncing off of the smooth surface and it's being reflected. Now we're going to also define a normal point to our surface, and that's going to help us define our angle of incidence and our angle of reflection. And if we have our wavefront, it doesn't matter where we are in our wavefront, it's going to behave that way. Now, we do utilize diffuse reflection. This is what's going to allow us to see the lines at the edge of the road, allows us to see our lines on our highways, allows us to do a number of things. But what we're doing to get that diffuse reflection is we have an uneven surface. We get that uneven surface and we still obey the law of reflection, but it's going to be highly dependent on exactly where our incident ray impacts our surface. And you can see what happens. We're going to get this diffuse kind of idea, and it's going to make things easier to see. So here's our normal line, here's our incident ray, and here's our reflected ray. And we've played with this. We've played with this before, in that if I take a ball and I bounce it off the wall, we're going to get that incident bounce and our reflected bounce. And these two angles are the same. Those two angles are going to stay the same. And so our law of reflection is that the angle of the reflected angle is equal to the angle of incidence. This will allow us to do periscopes. This will allow us to do reflecting up and down, backwards and forwards. This allows us to bounce light into various areas. And the big thing that you have to deal with here is just keep in touch with how that angle comes in and goes back. And I'll post the problem that I did earlier today so that you guys have it. And I've also got it in, there are other ones that are here as well. So what happens if it goes into the surface? That's when we refract. So here we've got our same incident ray, our same reflected ray, and now we go into the other medium and it's going to bend. Now this is looking at it and it's deriving that by looking at the speed. The speed of my ray is going to be impacted by my medium. But we're also going to see that we don't build up waves as it goes through. So we do get that dispersion effect, we get that separation. But this is also going to end up being our index of refraction. And our index of refraction is related to the change of the speed away from the speed of light based upon the material that the light is going into. If this is air, and this is glass, the index of refraction of air is less than that of glass. And what we're going to see is that the angle is going to bend towards the normal if my index of refraction is greater. It's going to bend away from the normal if my index of refraction is less. And you can have everything happen at the same time. So here's my incident ray. Here's my reflected ray. Here's my refracted ray. It's also being reflected, and here is being refracted again. So you see it bend towards the normal when it goes into the medium. It's bending away from the normal as it's coming out of the medium, because this lucite has a higher index of refraction than that of air. So we see this relationship. The sine of the angles have a relationship to my speeds, and that's going to end up being a constant. And we just talked about bending towards the normal and bending away from the normal. But what this is going to give us is that the index of refraction is defined as the speed of light in a vacuum divided by the speed of light in the medium. And we will start to see that change. For a vacuum, n is equal to 1. Air is very, very nearly 1. For other media, n is greater than 1, n is unitless. And as the value of n increases, the speed decreases, which kind of makes sense. But here's the thing. As light travels from one media to another, the frequency does not change. And both the wave speed and the wavelength do change to accommodate this so we don't stack it up. And we actually get a change in here, but the frequency is going to remain constant. So we end up with some ratios that we can play with, but most of the time we're just going to be dealing with Snell's law that we're in there. So you can see a variety of indexes of refraction. There's air. Like I said, it's very, very close to 1. Carbon dioxide is very close to 1, but we can also use our index of refraction in order to help us in organic chemistry as well, because in organic chemistry, we get lots of clear liquids, and there are volatile clear liquids, and it's really hard to tell the difference between benzene and ethyl alcohol, but you can see a difference with the index of refraction. So that's one way to identify things. So here's Snell's law. Don't make this any more complicated than it is. I mean, it's basically a ratio, and it's going to tell me whether it's going to bend towards or against. And when you do a couple of the homework problems and you have these in Blackboard, that you can actually go in and we change the layer of the indexes of refraction change. You can look at it from that point of view. So you can look at those. So the index of refraction in anything except a vacuum depends on the wavelength of light. So this is going to allow my prism to spread the light. This is going to give me dispersion. This is going to help me with diffraction gratings. And that's what's going to give me my rainbow or my thin film images. So you can actually see how the different colors are going to behave as we utilize the index of refraction. And here is our angle of deviation that we get from our prism, which is going to allow us to spread our white light and see that white light is made up of red, green, yellow, blue, indigo, and violet. So you can get all of those things. We can utilize this to give us our spectrophotometer. This is going to allow us to look at absorption spectra. It's going to allow us to look at emission spectra, because now we can go back and look at the hydrogen spectra and the helium spectra. We can go there. It gives us our wavelengths of gas, give us a fingerprint so we can find those. The rainbow acts like a prism. Our raindrops are going to act like a prism, which is going to give us that dispersion, which allows us to form our rainbow. And then you've got a nice picture of a 2-order rainbow here, where you're getting it from the refraction. So as we've said before, Huygens gives us that wavefront, and we can use that construction. So any spot gives us a new wavefront that we can utilize. So we've seen this with sound. This is not anything new. This is just, now we're going to remind you about that in terms of light, because now we can play with geometry and use that reflection and be able, and Huygens actually was able to prove Snell's law using geometry. So that way we can look at those pieces. So you can go through. And finally, there is a point where the light can't get through the surface. And that's our critical angle. And if you've ever been sitting at the bottom of the swimming pool and you look up to the top of the water and you'll see a mirrored like area up there, that's where we're going to get that total internal reflection. And that's what's going to allow us to have fiber optics. So we're going to get a critical angle. So at some point, we're going to get a critical angle where it just can't go through. And we're going to get total internal reflection. And that's going to allow us to have our fiber optic. So, and that's for any angles greater than the critical angle, the beam is completely reflected back in. So you get that part in there. And so now you can have your fiber optics, which just utilizes that total internal reflection. So that's our transition. I'm going to open it up for questions. I'm going to stop my share here. All right. I'll open it up for any questions, and I'll get this video posted later on. but